natural question arises in vectors. That is, what happens to the direction and magnitude of a vector when it is multiplied by a scalar quantity. So here you can see that the product of a vector A by the scalar constant, say lambda, is given by what? The lambda into vector A. So that is, you multiply lambda with what? The vector A. And where lambda A is called as what? A vector. It is a new vector. To deal with this, consider vector A. Here A is a vector that has magnitude how much? 4. Then 2A is a vector that has magnitude how much? 8. That is, magnitude of lambda A, which is nothing but lambda A will be lambda into the vector A. So that is how we multiply a scalar with a vector. Now, to understand what happens to the direction of the new vector, that is lambda A, consider the following vectors. That is, here we can observe that when the vector A is multiplied by a positive scalar, that is by 2, what happens? The direction remains the same. The direction reverses when it is multiplied by a negative half, that is minus 1 by 2. Thus, direction of the new vector lambda A depends on the sign of lambda. If lambda is positive, then direction of lambda is same as that of the vector A. If lambda is negative, the lambda A has a direction opposite to that of the vector A. So remember this carefully. Now it is important for us to understand about additive inverse of a vector A. The additive inverse of a vector A is a vector having magnitude equal to the magnitude of A and direction opposite to that of the direction of A. Now to obtain additive inverse, we have to multiply the given vector A by a scalar, and the scalar is nothing but negative 1. That is, when lambda is equal to minus 1, then lambda A is nothing but minus A, which is the additive inverse of the vector A. So far we have been discussing about scalar vector interaction and its associated properties. You might have already learned about unit vectors, haven't you? Here we have to discuss about an unit vector in the same direction of given vector. To find a unit vector in the same direction of a given vector, we have to divide the vector by its magnitude. Since we have learned this much, let me ask you a question. We have learned that a vector can be multiplied by a scalar. So now the question is, can you multiply a scalar quantity by a vector? Stop wondering and start thinking. Have you got? Well, the answer to this question is no. A scalar quantity cannot be multiplied by a vector. Now our objective is to understand about the components of a vector. The components of a vector in two-dimensional coordinate system are usually considered to be x component and the y component, whereas in three-dimensional space it will be the x component, y component, z component. To understand this better, let us look at an example. You know that any natural number is just the number 1 added to itself a few times. Similarly, for vectors, there exist some special vectors such as I cap, j cap, k cap, such that a vector can be expressed in terms of these special vectors. Here I cap, j cap, k cap are unit vectors along the axis, which is OX, OY and OZ respectively. For example, consider a vector R in the 3D space. Then it can be decomposed as the addition of these vectors, that is I cap, j cap, k cap and the suitable x, y and z components. Here vector R can be written as xi plus yj plus zk. This form of any vector is called as the component form of a vector. One should note that x, y and z are called as the scalar components of the vector R, and x, I, y, j, z and k are called as the vector components of vector R along the respective axis. Here one should note that to obtain the length of vector R, we have to take the square root of the sum of squares of components x, y and z. Now we have to deal with some basic properties of vectors based on the understanding of component form of vectors. We just studied the component form of vectors. So if vector A and B are any two vectors in the component form, a1i plus a2j plus a3k and b1i plus b2j plus b3k respectively, then the addition and subtraction of these two vectors can be done easily by adding and subtracting the components as mentioned here. Have a look at it. Now you understand the addition and subtraction of vectors given in the component form. Now you might have thought about the situation where two vectors are equal. Well, two vectors A and B are said to be equal. That is, if A1 is equal to B1, A2 is equal to B2 and A3 is equal to B3. Similarly, to multiply the vector A by any scalar lambda, we have to multiply each component of vector A by how much? Lambda. Further, the addition of vectors and the multiplication of a vector by a scalar together gives what? The distributive law. Let's take a vector A and B are any two vectors and K and M be the two scalars. Then Ka plus Ma, that is you are multiplying with A, what? K as well as M. So you get K plus M into vector A, and that will be equal to Ka plus Kb, or K into A plus B will be the same as what? Ka plus Kb. Now let's deal with another important concept. Look at the figure. Here, vector P1, P2 represents a vector obtained by the joint points of which one? P1 and P2. The points P1 and P2 are joined with the origin. Now by applying the triangle of vector addition, we obtain OP1 plus P1 P2 will be equal to what? OP2. And thus we can also say P1 P2 will be equal to OP2 minus OP1. Also we can say P1 P2 is equal to x2i plus y2j plus z2k minus x1i plus y1j plus z1k. This is also equal to x2 minus x1i plus y2 minus y1j plus z2 minus z1k. As you can see, P1 P2 obtained by subtracting the corresponding components. So we have used the components and we have found out what is the vector P1 P2. Now it is time for us to discuss another important topics. What is that? The section formula. For that, consider 2 points P and Q. Here OP and OQ represent the position vectors with respect to the origin O. Then the line segment joining the points P and Q may be divided by a third point, say R, in two ways, which can be either internally or externally. Now we are going to find out the position vector for the point R with respect to the origin in both the cases one by one. Let's find out for internal as well as the external one. Considering the first case, that is R dividing PQ internally. The figure given in the screen represents what? The internal division here. Have a look at this one. Let OP be a vector which one? A, OQ be another vector B, and OR be another vector R. Also, R divides PQ internally in the ratio m is to n. The ratio is given there as m is to n. Then position vector of R is given by the formula, which is nothing but R is equal to mb plus na, the whole divided by m plus n. So remember this formula, that is to find out the division, we have to just take this formula mb plus na, the whole divided by m plus n. Here we have to note that if R divides PQ internally such that R is a midpoint of PQ, then m is to n becomes what? 1 is to n, that the ratio is same. Applying this ratio to the equation of position vector of R gives you the another one, that is the formula R is equal to what? A plus B by 2. So if it is a midpoint, then you just have to use a formula that is A plus B by 2. Now let us understand the second case, that is R dividing PQ externally. So it is an external division. The figure for external division is given here. From the figure, position vector of R becomes what? Not mb plus na by m plus n, it becomes what? mb minus na by m minus n. So that is about internal division and external division, and we have discussed what? The section formula. So far we have discussed various aspects related to scalar multiplication of vectors. Can you point out any application of multiplying a vector with a scalar? Let me give you one. Many SI units of vector quantities are the products of the vector and what? Scalars. For example, the SI unit of velocity is meter per second. Velocity is a vector quantity. This is obtained by multiplying the two scalar quantities, length and time, with a unit vector in a specific direction. There are many other instances in mathematics and physics where vector multiplication with a scalar is used. Find out more such interesting examples and expand your horizon of knowledge. We will further navigate through the world of vector algebra in the next video. Now let's have a quick recap.
Manorama Horizon, learning made simple.